We are extremely fortunate to have with us a systems guru of the stature of Professor H.K. Kesavan, founder chairman of the Department of Systems Design Engineering at University of Waterloo. Professor Kesavan received his undergraduate degrees in Science and Engineering from the Central College and the Government Engineering College, Bangalore, and his postgraduate degrees in Electrical Engineering from the University of Illinois and Michigan State University. During his career, he has served as chairman of Electrical Engineering at the University of Waterloo and later as the founding chairman of the Department of Systems Design Engineering. In between, for a period of 5 years, he served as chairman of Electrical Engineering at the Indian Institute of Technology, Kanpur, and concurrently as head of its computer center. He was also the first dean of research and development at IIT Kanpur. He has published numerous technical papers and books on systems theory, applications of linear graph theory, and entropy optimization principles. Professor Kesavan has maintained a lifelong interest in the philosophical aspects of science. His book, Science and Spirituality, presents a global view of Vedic philosophy from the insights that science and spirituality provide. DI was privileged to confer Professor Kesavan with the Lifetime Achievement Award during the Joint International Conference on Applied Systems Research and 33rd National Systems Conference in November 2009. All of us cherish the video recorded acceptance speech delivered by Professor Kesavan, and his award was delivered at Waterloo by Professor Peter Rowe, another stalwart in the systems field, groomed by Professor H.K. Kesavan. We request Professor Kesavan to enlighten us with his vision talk entitled System Theory as an Academic Discipline, Some Reminiscences.
Professor Satsangi, distinguished members of the DAI faculty, and dear students. It's a great pleasure to accept your invitation and participate in this conference. Vishal Sani has praised me actually and heaped many accolades. Whenever, of course, when somebody gives such tributes, it's always music to your ears. But then the difficult task starts to rise up to that expectation. So I'll try my best to convey the idea about system theory. It's a very broad subject. I did not come prepared actually with a PowerPoint presentation. For one thing, I'm an octogenarian, used to my old method of actually a blackboard and a piece of chalk to convey ideas. And although I use PowerPoint lately, but I did not do so this time because I was not very sure of the audience, so I did not it was not a prepared lecture that way. So I see listening to some papers just this morning, I see many girls actually presenting this one, which pleases me. So I am confident the time has come for the passage of the Women's Rights Bill. So talking about system theory, when you're talking about reminiscences, I will give you some of my own personal anecdotes, because that is the only way perhaps to convey a large field in a short time. Long time ago, I went to the University of Illinois in the 50s, and the choice of the University of Illinois was purely accidental. I went there after my BSc, BE, and working for the US in Bangalore and all that. Then at that time, like many electrical engineers, I also wanted to do some power engineering, because you know those days in many of the Indian universities, electronics was still a new field, and I was trained as a power engineer. So when I went there, the Dean of Engineering there was one Dean Ryder, and he said, the age of the power engineer has come to an end. He said, and like the dream of Cinderella coming to an end at the stroke of 12, power engineering also has come to an end. This was the categorical statement that he made, because those were the days when there was so much of enthusiasm for electronics and communications. Of course, he was wrong in his statement, because power engineering is very much alive, and in fact, it's one of the fascinating fields that one has to study these days. So I went actually into network theory, and at that time one of the biggest exponents of network theory at the University of Illinois happened to be Dr. Sundaram Seshu. You must have seen many of these books, Seshu and Reed. And Seshu, I think the Indians can be proud of this one because, you know, his grandfather was Right Honorable Srinivas Shastri. And I think many people who know the political movement of India those days would know Right Honorable Srinivas Shastri. So he's a very good lineage. I remember one thing about Right Honorable Srinivas Shastri. When the statement was made that the sun never sets in the British Empire, this man got up and said, because God will never trust the British in the dark. So he was an orator, immediate, repartee and all these things. So he came from this kind of lineage, and he was a brilliant, absolutely brilliant electrical engineer. Unfortunately, he died in a car accident at a very early age. So he, in fact, induced me to take up network theory, and that is the time when I learned graph theory and electrical networks, which opened up a new vista of possibilities completely. Of course, along with that one, of course, mathematics and matrix algebra, differential equations, Laplace transforms, and many of these things. And so then after doing all this network theory, I came into contact with Hermann Koenig, whom Professor Satsangi knows him very well. And so Koenig, you see, was not satisfied with the application of graph theory. Graph theory, is, in fact, the last paper referred to graph theory, and I was very pleased the person who presented the paper also referred to a paper by Savage, who was my student, in fact. So in application of graph theory to magnetic. The thing is, Professor Koenig very much wanted the application of graph theory to be extended to electromechanical systems, because he came as a power engineer, and then he wanted actually the application to be extended to electromechanical systems. And that was where, of course, you see, he got me into it. And then it went on. Of course, we went to mechanical systems. In mechanical systems, we not only dealt with one-dimensional mechanical systems, kinematics, and three-dimensional mechanical systems. Then we went to hydraulic systems, thermal systems, so many of these things. So what has to be stressed here is that system theory is a subject. See, if you take all the engineering disciplines, I confine myself to engineering disciplines for the present, there's one end of the spectrum which deals with systems. And you will see, because of the economies of curriculum, there is not much emphasis given to the core concept of system theory in any one of the engineering disciplines. So these concepts are mighty important. It gives you a common intellectual focus, some common intellectual origin to look at a disparate set of disciplines. This is what system theory does. And it just turns out that for deterministic systems, by deterministic systems, I think to this audience I can make a very short statement. These are systems which can be described by algebraic and differential equations. Okay, deterministic systems where there's a cause and effect relationships and so forth. So these things can be handled by means of graph theory. The graph theory is a part of combinatorial topology, but the part of graph theory that we dealt with is actually makes use of what the definition of a element of a linear graph is. So I don't want to go into the details, but what it is, it gives a very powerful tool actually to comprehend these things. So one other thing which has to be emphasized is, we would not have made such big strides in the understanding of physical systems on the basis of these concepts, but for the advent of digital computers. It's a very propitious thing that happened. So the ideas which were generated by computers and system theory, there was in fact a clear congruence of ideas. And so one helped the other, and we were able to, in fact, come up with many computer ideas for the formalism. This is the point that has to be stressed here again. It's a broad point. You know, many of the physical systems, there's an analytical and a theoretical way of formulating the problems. And you run to your computer, only you come to the stage of solution. That was of course, the early days of computers. This is what was being done. You formulate the problem completely the way that you do it in theoretically, and then you think of the computer for the solution of the problem. But that is not a wise way or a good way of, or efficient way of making use of computers. The way is, of course, having computer in mind, how do you reformulate the problem actually, so that computer is used both for formulation and solution. It is in this broader idea, very precise idea, that graph theoretic formulation of physical systems came in very handy. So I'll say this much about the discrete the deterministic systems. And then, so that's a broad area, I will confine this one. Then I will go to, let's say, probabilistic systems. It's a completely different field altogether. By probabilistic systems, what I mean is the following. These are not, for this one, of course, the mathematical tools that are used are statistics and probability. So, in the late 50s and the early 60s, there was one Professor Janes in Washington's University in St. Louis. He is a theoretical physicist. He came up with the idea of what is called as Janes formalism. Here is the idea of Janes formalism. See, you know, it combines, of course, several ideas. You first of all, you start with Shannon's information measure. Shannon is a professor in electrical engineering. When I was at IIT Kanpur, and it just turns out one of the heads of electrical engineering department at MIT was also a member of my department. This is Professor Louis Mullen. He used to tell me lots of stories about Shannon. Shannon, everyone thinks about actually a very theoretical man, but he was actually tinkering with many things in his basement actually. And when he was working in Bell Lab, he came up with his famous Shannon information theoretic measure, minus pi, sigma, pi, log, pi. That is a measure. And why did he come up with this one? His idea was to codify actually many of the things actually compared to communication theory. The communication theory, various ideas, transmission of signals, modulation, and so forth. All these things actually were codified on the basis of actually the Shannon's information measure. The famous paper was Shannon and Weaver, and I think he wrote only a very few papers, but each one of them is worth its weight in gold. And one of those things, and he almost revolutionized the whole field. But he did not make use of one very important concept of Shannon's entropy measure. And that is, Shannon's entropy is a concave function, and since it's a concave function, it is a global maximum. So he made use of this one, and he was able to derive all the important distributions of statistical mechanics, like Maxwell-Boltzmann distribution, Fermi-Dirac distribution, Bose-Einstein distribution, many of these things very systematically on the basis of optimizing the Shannon's entropy measure with respect to different sets of constraints. It's a remarkable achievement, actually, this one. So, what does it do? I have talked to some physicists who have written books on statistical mechanics, teach them a little bit, where is the physics in it? Because you take the Shannon's measure, You take constraints, you optimize them, and you get those distributions. Why do you actually wrangle so much of it? So this is a different story altogether. But what it does conceptually is what this is very important to understand. This actually combines the idea of statistics, probability, and information theory. You see, this is very important to recognize because people think that only statistics and probability are related. If you take, say, let's say, bell curve. Bell curve, if you just take, you see, they would say it appears in nature. If you just wave our hands, it appears in nature. No. You see, if you take Shannon's entropy measure, and if you optimize it with respect to mean and variance, you get the bell curve. That means you are combining, you are establishing the link between probability, statistics, and information theory. So it stands in a tripod, you see, and it is this concept which has given us actually some sweeping power actually to deal with actually probabilistic systems. You know, Professor Jane Kapoor, who was in fact head of the department in IIT Kanpur, was a colleague of mine, and later on, I think he was also the president of the Indian Mathematical Society and all. Professor Satsangi would know all the details. The thing is, he was, I invited him several summers actually to to Waterloo, and we wrote actually a book together. And see, when I did not take even a graduate student at that time because I was not certain whether I would be doing justice to the graduate students because my ideas were still formulating. But it just turns out those ideas have been used for the understanding of many probabilistic systems. I'll say this much because problems today are dealing with time series. Like for instance, even starting with stock market, you can formulate actually probably on the basis of these things. Traffic engineering, somebody mentioned this also could be done in terms of entropy measure. So the whole subject of probabilistic systems, I think it just gives you a very good idea of dealing with these problems. One other thing which I will say, this is for research purposes and so forth. You know, the whole idea of pattern recognition has become very important. But how do you see patterns if you get various data and all that? How do you get patterns out of these things? There is some innate structure in the whole thing, you see? And my own feeling is, this is not a feeling, I think it's more than, I think I would say it's a conviction, but it's still to be tested very clearly. And I will tell you what the difficulty is. That is, if you take Shannon's measure, you see, I told you it's a concave function, it's a global maximum. But if you minimize it, you will get into patterns, various patterns. We are able to actually show, you know, connection with many statistical ideas in this one, the minimization of this function. So again, it could be applied, and but there is a very serious mathematical problem because while it is easy to find a global maximum of a concave function, it is very difficult actually to find a minimum of a concave function. So it's a computer difficulty and all that. Okay, I will leave that much there. Then we're going back actually to one other thing which I should not miss, particularly this audience, because the graph theory and all that was not only confined to physical systems, but also we try to do it for socio-economic systems. One of the first theses that came out, actually application of graph theory to economic systems, was by Professor Satsangi. And it was a remarkable opening actually, this one. He was able to show many of the macroeconomic models actually in a very systematic way by use of graph theory. See? And I was encouraged because of this one to try and do other things for the other socio-economic problems. But the socio-economic problems don't come that easily, because there are a set of problems which lie at the interface of science and technology on one hand and society on the other. For those problems, you see, we had to go for other mathematical models like conflict analysis and all. I saw by reading some of the papers that are presented in this conference, people have referred to some of these models, actually, these things, conflict analysis and all that. So that's a different area altogether. So in my own experience, there is one thing which I do as in a department head of systems design and all that. How do you convey these ideas to our students? So we had in our curriculum about 1/6 of the undergraduate curriculum almost devoted to what we call as systems design workshops. By that I mean you choose socio-economic problems of graded complexity and then form teams of students actually to tackle these problems. See? And first of all, give them the ideas of what system theory is, basic concepts. Then the idea of design also should be given. Because you see, usually what happens is, to find a solution to a complex problem, the solution is very close to the definition of the problem. See, you have to define the problem very clearly. And how do you, with increasing levels of refinement, how do you define actually a particular problem? That is extremely important. So we made use of the opportunity of a place like Waterloo. We could invite, because there are many visitors to Toronto, just like in Agra, I'm sure your proximity to Delhi and other places, you see, you will have access to many people, eminent people in the various fields and all that. They could give you, some one-day lectures to students and all that. I can develop actually these things and all that. So I would just leave the thought that to this one, this is an extremely important thing. And I think many of the students' theses, particularly if they persist to that problem on the third and the fourth year also, at least for 2-3 terms, in fact, they got to a stage where they could publish those papers. Although the idea was not just publication, but it gives you an in-depth understanding of what system theory is if they really work on such problems. That is another system design. So, to sum up till now, what I have done is, I have talked about discrete physical systems, I have talked about probabilistic systems, and also referred to the possibility of application of these things to socio-economic systems. So, I will also, particularly in this institute, I think it's extremely important, I thought, because you have shown the way actually already. We are talking about the philosophical systems and all that. I'm a great believer in one thing, because I've been a professor who also taught teaching abroad, and many of the Indian students have come and talked to me. They want to know something about their own past. They want to know what the philosophical moorings are actually of our own scriptures and many of these things. Because not all parents can give them guidance, and they don't have any classical education. How do you actually convey some of these ideas to these students? I know that from experience, what I'm going to say is not merely confined to students abroad, these things. See, because many Indians, we learn many of these things about philosophy and many of these things through osmosis. Whatever there is, we pick up. And one thing very interesting about Indian philosophy is everyone thinks that he knows about it already. See? And it needs some in-depth understanding of these things. So I believe science and technology, particularly training in science and technology, can provide very sharp pointers to the understanding of the basic concepts of Indian philosophy. I won't say, you have to be very careful here, that science and philosophy will give an understanding. I said short pointers. It's just like this. If I say the moon is at the tip of the arrow, you see, if I just point out, you see, you know that the moon is not at the tip of the arrow, but it's giving you pointers, short pointers. So like that, many pointers actually we can get, actually, I think, from science and philosophy. And I'm convinced of this one because there is also another thing. See, we hear discourses on philosophy, Indian philosophy. That is, somebody gives a lecture, let's say chapter 2 of the Bhagavad Gita or something like that, another chapter 16, another. But there is no systematic learning. There is no systematic learning. Unless, like anything else, I think you have to have a systematic distinct expression of it for a length of time from a competent guru. So these are the three things which is necessary. And I think this can be done. And what I really appreciate about Dayal is actually from you have already tried to accomplish some of these things, and you have made use of science and technological means, mount courses actually, which are available actually, not only within your institution but abroad. And I think this could be a very special and unique feature of Dayal. Sorry. See? And not many people would do that one because there is a great deal of confusion. You are bringing religion into your courses, that, this and all that. No, none at all, you see, because all these things are the kernel of every religion for that matter. It is very secular, if you want to use that word, you see. And you know, in Western world, yoga philosophy has been accepted as something secular and all that. But beyond that, you see, there are many powerful ideas here, see. And I think these things, an institution like that, which has already made some headway, I think we should explore this idea even further, I think, because, and the means of actually many of these things, the technological means, and I think the other people, there's a very hungry audience, believe me, outside, for this particular institute and all. Why you go outside, even here, I would say, talking about, because I go around in Bangalore, I know that what I've said is equally applicable here and all that. So this is something that you can look into, and I think, again, to repeat, science and technology can provide sharp pointers to the understanding of our scriptural knowledge. And I think this is very important to learn because, and it's all not theoretical, because I know that you're already complementing it meditation and all that, which is extremely important. I will go at that one, and I'm absolutely convinced about these things. So we implemented that in my own life and many of the friends and all that. And so that will be a different discourse altogether, but I think this is a unique feature in all these things. So see, one of the things that we might also point out is, I'm not deviating from system theory, system science and all that. See, we have, I will tell you another personal experience. We started actually, you know, in this conflict-ridden world, I think an understanding of our philosophical moorings are extremely important. Therefore, we started out by saying that the main kernel of all religions, you know, there is a commonality in it. So we formed a group, okay? There were Hindus, there were Christians, you see, and the Jews. So we have formed a group actually in this thing. Unfortunately, we were not able to get somebody from Islam. I'll tell you why, the reason and all these things. I have reason for that one. But we have developed our own understanding about these things. So what I have found, of course, from this experience is that even here, if you want to have an understanding between different religions and all that, it is not, the understanding can come only at the summit. That is, people who are well versed in particular religion only should talk to somebody who is well versed, then there's an understanding. In between, there's a lot of confusion. See? So, And one of the things that makes it easy for us, of course, I would say for Hindus, is because of a firm conviction of inclusivity, which is not there in the Judeo-Christian religion. See, by inclusivity means we would accept, of course, you see, there might be other ways of realizing, self-realization. Okay, we won't come in the way. I mean, within Hinduism itself, we have that understanding and all that. Whereas in the case of Christianity, again, there was a difficulty there. You see, because it's always through so and so. But what toned it down, of course, this difficulty in the case of Christianity is because they also subscribe to science and technology. So the spirit of Renaissance, the spirit of rationality, and all these things are there. Therefore, there's a lot of actually, understanding about what the other faiths do to give them freedom to do that one. This is what has happened in the Christian world. But this has not happened in Islam, because they have not embraced science and technology to the extent they have done. You see? That is the main difficulty. And I think if the deep discussion should take place at that level, seems to me, to bring in some amelioration. I'm not talking only about the Indian, all over the world. One thing that I find is, if there is a problem like that in India, don't think that I'm getting into a political discussion, because this is very important. If there is a specific problem, this specific problem is merged into a larger class of problems because it's felt all over the world right now. And there is a solution for it if you do go about it intelligently. So, I think I've given you a large sweep of ideas, many of these things. I will just say that I'm very, very, very pleased that system theory, system sciences have found a firm footing in this institution. And I'm also mighty pleased, of course, by the philosophical ambience of this place. And that ambience is extremely important. And you already started actually trying to convey these things, articulate on these things, mount courses and all that. So I think this aspect, if it is even strengthened further, you will be establishing your own uniqueness and actually serving actually a great cause. Thank you very much.